what we have seen so far is still used in reinforcement learning, but it's like a tiny part of it. So there's one step where you use all those considerations about supervised learning, but in general, it feels much different. Okay, so these are the resources I would recommend to someone who wants to learn about it. The first one is a book. So the first edition of the book is from the 80s, and it's a classic. And the second edition, well, everything I will explain, I learned from this reference. And I think it's a really nice book. And then there's this website from OpenAI. OpenAI is a big company in this area, and they have a sub website where they give an introduction to reinforcement learning. I think it's quite nice. Okay, so the definition from Wikipedia about reinforcement learning is that it is the branch of machine learning that is concerned with how agents should take actions in an environment in order to optimize some cumulative reward. So this became famous in 2013 when in a paper it was published how to train an agent to play any Atari video game from scratch without knowing anything, just by playing by itself, without even knowing the rules of the game. The agent, the robot, just had the controller, and just by trial and error and seeing the rewards it was obtaining, it learned to play the video games, many of them at superhuman level. And the algorithm they published is called DQN, Deep Q Networks. It is one of the algorithms I want to describe. So here's a short video where you can see it is described how the agent learned to play the following game. So they start with 10 minutes of training when the agent basically doesn't know to do much. It's kind of confused. Then after 2 hours, it's very good. Not bad. But then after 4 hours, it realizes that if it breaks one side of the wall, then it is very easy to win the game, like it did in here. So here it tried to attack this part of the wall, which makes it much easier to end up winning. Okay, then in 2017 there was a groundbreaking result. Some guys in the same company, DeepMind, which is a company from Google, it was bought by Google. They published the AlphaZero algorithm, which is it's used to train an agent that was used to play Go, chess, and shogi. Shogi is some kind of Japanese chess. It's similar to chess. It's a Japanese game, ancient game. This was a big deal for the game of Go, because by that time it was an open problem to create an artificial intelligence that played Go at superhuman level, or even at the best human level. But this algorithm learned to do it. It defeated the world champion of Go in a series of games. And what is kind of surprising is that it just learned to play by playing by itself. It just knew the rules of the game and nothing else. So if you are interested in chess, you can check the games of AlphaZero against Stockfish. Stockfish was the AI before AlphaZero, that was the strongest AI before AlphaZero, which is based on, Stockfish is highly engineered. It's based on, it comes from a lot of work. It's an old program that has been evolved and improved over many years. And so there are several games published between AlphaZero and Stockfish, and if you see them with commentary, it's quite entertaining, even if you don't know much about chess like me. Okay, so what do we do to model the problem? We want to study the problem in general terms, and for this we use a so-called Markov decision process. This is a tuple where S is a set of states, just some set. Some of the states are initial and some are final, S0 as F. For simplicity, we will assume that there's just one initial state, which I call S0. R is a set of rewards. A is a set of actions. For each state, there is a subset of valid actions. For that state, the set of valid actions you can apply. If you think about chess, for example, there's sometimes you can castle and sometimes you cannot castle. So in some states, castling is not a valid action. But this is the matter about valid actions is just a technicality. I will ignore it in this talk because I just want to convey the main points, not get into too much details. The states, the actions, and the rewards can be finite, infinite countable, or continuously infinite. The R is a map from pairs of states and actions to rewards. It specifies the reward you obtain after taking an action A when you are at state S. And rho is the dynamics map of the whole system. It's a rho maps a tuple from S cross A, so a pair state action to a state to a new state. And what it means is if rho of SA is S prime, this means that the effect of taking action A at state S is to change the environment to state S prime. Okay, so rho is not really a map. It's actually a probability distribution. So it maps each pair, state, and action to a probability distribution over the set of states. So this means that rho SA is just it just assigns probabilities to which state you will get next if you choose action A at state S. So we denote, in this case, since it's a probability distribution, we denote rho SA as in this form as a conditional probability that depends on state and action. And then rho of S prime, depending on SA, denotes the probability of moving to state S prime after taking action A at state S. And we are going to write S prime, this symbol from this distribution to denote that S prime is sampled from the distribution. Also, the reward map, you could make it stochastic, but we're not going to do this. It's not difficult to do it. And okay, there's many variations. You can formulate Markov decision process in several different ways. In general, they are all equivalent. The formulation I gave is very flexible. It really allows to accommodate all sorts of settings, but maybe for some specific settings you need to modify it a little bit. But in the end, it's really equivalent. Okay, so rho completely determines the dynamics of the Markov decision process, and then observe that as we defined, according to our definition, the effect of taking an action A at a given state S depends only on the state. So it depends only on rho and on the reward map R. And it doesn't matter what you have been doing before. So when this happens, this is called the Markov property. In many environments don't behave in a Markovian way. For example, if you think of chess is very Markovian, because when you reach a state, it doesn't really matter. When you reach a board position, it doesn't really matter what has happened before. To end up winning, you just have to look at the board position and try to win from there. It doesn't matter what has happened before, except when there are three pairs of moves in a row, in which case the game is tied. So if you are in a board position and the same two pair of moves have been played in the previous moves, if you continue playing like this, the game will be a draw. So in this sense, it's not Markovian. But anyway, this setting is applied in many environments. Some of them are more Markovian than others. It ends up working, apparently. So we will continue with this assumption of the Markov property. Okay, so if the dynamics map is a degenerate distribution, then we say that the MDP is deterministic. And by degenerate, I mean that the distribution assigns probability 1 to one specific event and 0 to the rest. And here are some examples of Markov decision process. Just examples of how you could formulate problems as an MDP. For example, the problem of solving a Rubik's Cube. You could say that the set of states is all possible Rubik's Cube combinations. Your actions are the ones listed here. And the initial state is any cube combination. And the final state is the cube when it is solved. And then you give rewards. You always give reward 0, except when you solve the cube, and then you give a reward of 1. That's a possible way you could formulate the problem of solving a Rubik's Cube. Solving a Rubik's Cube is actually a problem that is studied in reinforcement learning research. Another example, you can formulate the problem of creating a robot that drives a car as a Markov decision process. So the states would be road, street street situations. The actions could be pressing the brake, pressing the accelerator, turning the wheel, and so on. And the rewards could be -1 if you run over a person, 1 if you reach your destination. In this example, we have that the set of states and actions is continuous. This is an important distinction. There's algorithms that only work for discrete settings and some that only work for continuous settings. Okay. Let's continue with our formalization. So we have a Markov decision process, and now I'll define what's a trajectory. A trajectory is just a sequence, tau. The sequence contains triples. And what's each triple? Each triple contains a state, an action, and a reward. This, and then the idea is that this trajectory is you start at S0, and then you choose some action, and then R1 is the reward you obtain when you choose A1 at state S0. And S1 is sampled from the distribution from row S0, A1. Right, so it's just trajectory is like you do an event of the problem you want to solve. So you start at the initial state, choose an action, you get a reward R1 according to the reward function. Then you move to a new state S1. The new state you move to is controlled by the row. Here, this R should be, this Ri plus 1 should be little r of Si A plus 1. There's a notation typo here. And you continue until you reach a final state. This can also be called an episode. Theoretically, trajectories can be infinite, but I'm going to ignore this here. It's quite common in when you study MDPs from a theoretical viewpoint. It's common to use infinite trajectories, but of course in practice you cannot. Okay, so I'll just ignore this. So what is the return of an episode? This is you take a trajectory or an episode, and the return of the episode tau is just the sum of the rewards in the triples. And usually you use a discount factor, which is a constant from 0 to 1, very close to 1 usually, and you define the return as this weighted sum. So you weight each reward by gamma to the I. So the first reward receives a 0 weight, a 1 weight. The second reward receives a weight of gamma, the second one gamma square, and so on. The idea is that in this way, the same reward has more value if you receive it today than 3 years in the future. So if you don't do this, and the episode can go on for a long time, the agent doesn't really care about getting the same reward right now or just very, very, very far away in time. Okay, so just a word about designing reward signals. So the agents want to maximize rewards, right? I didn't formalize this, but I will in the next slides. But for the moment, we know that agents want to maximize reward. So this can be tricky. For example, consider the following example. Suppose that an agent is meant to sweep floors, and you decide to give it 1 point every time it sweeps 1 square meter of floor. So the agent starts its task, and eventually it discovers that if it sweeps and then spills over the dirt on the floor, and then it sweeps again and so on, it gets a huge return. So this is a fail case. It might be an unexpected behavior. And yeah, it's not hard to imagine more serious fail cases similar to this one. For example, a robot nurse that consecutively makes the patient ill, and then it cures the patient, and so on. Okay, let's continue with formalities. So a policy pi is a map from the set of states to the set of probability distribution over actions. We want policies to be the rules by which the agent acts. So pi of S is a probability distribution over the set of actions. We write it as pi dot conditional on S using conditional probability notation. And then pi of AS, where A is an action, is the probability assigned to action A when in state S. So this means that if you are in state S and you are an agent following policy pi, you should choose action A with probability pi AS. Again, I will use this notation, sampling from this distribution. If the policy is degenerate, then we will say that it is deterministic. And then we just look at it as a map from states to actions. Okay, so now the goal is to formalize what the agent must do, what the agent has to achieve in a Markov decision process. First, observe that if you have a policy, then you obtain a distribution over all possible trajectories. Why? So take a trajectory. Again, this is you start at the initial state, decide some action, you receive a reward, you move to a new state according to the dynamics of the MDP. You decide a new action, A2, get a new reward, and so on until you reach a final state. So assume we have a trajectory and a policy. And now we can speak about the probability of this trajectory according to this policy. Oops, I thought I put pauses here. Okay, so the probability of tau given pi is the following. What is the probability that following the process I just explained for obtaining tau, you end up with this tau? So first of all, to obtain A1, the probability that at state S0 you decide to take action A1 is given by this value in here because you are following policy pi. So this is the probability that you choose A1. Now, the probability that you land in S1, so that your next state is S1, is controlled by the dynamics map, rho, and it is rho of S1 conditional on S0 A1. Okay, now we assume we reach S1, and now the probability of choosing A2 according to policy pi when at S1 is given by this number. So we multiply what we had before by the probability that now we choose A2. Now we multiply by the probability that now we reach S2, and so on, until we are done with all the triples in the trajectory. And we end up with this expression. And this is the probability of choosing tau if you are following policy pi. And then now we can speak about the expected return of the policy, which is simply the expected return of a trajectory when you follow trajectories according to the policy pi. So it's just, if you are in a discrete environment, here you have a sum. If you are in a continuous environment, here there's an integral. It's just the weighted sum of all returns of trajectories, and the weights are the probabilities of selecting the trajectory. There were pauses, but it wasn't, it's weird, okay. So the goal of the agent, the goal of reinforcement learning is to find a policy pi that maximizes the expected return as we define it right now. Such a policy is called an optimal policy. It might not be unique, but we will assume it's unique for simplicity. Doesn't really matter. And the optimal policy is denoted by star. Okay, some more definitions, and then we move to less formal, less definition territory. So given a policy pi and a state S of the MDP, you can ask what's the value of that state, in which sense. So if you have a policy pi and a state, you can ask what's the expected return I would get if I start at this state and follow policy pi. And this is called the value of the state with respect to the policy. It's denoted v pi of s, and it's just the expected value of the return of a trajectory when the initial state is s. And similarly, you can define the value of a state action pair as A as the expected return of a trajectory if the initial state is S and the first action taken is A. This is called a Q value. Okay, so now, oh, I didn't say my goal is to explain the DQN algorithm and AlphaZero algorithm in this talk and the next one. So now I will discuss a little bit different types of reinforcement learning algorithms, and then I will start explaining the first notions needed for the DQN algorithm, and I will finish the explanation of DQN in the next talk. Okay, so types of reinforcement learning algorithms. A key distinction is if the agent knows the dynamics map rho and the reward map R. So, for example, if you are trying to solve a Rubik's cube, then you can think that the agent knows the dynamics, that the agent knows what its actions will do on the environment because he knows the rules. So it's a reasonable assumption. So if you know the model, so you know the probability that if you take certain action, you get a certain state and so on. So if you have this information, the agent can, before choosing an action, it can plan ahead because it can run simulations of future events induced by its actions because it knows how the model responds to actions. If it doesn't know how the model responds to actions, it cannot simulate before moving. For example, the Rubik's cube, and then chess is also widely put as an example of an environment where the agent knows the model. It is a little tricky and sketchy because you don't really, if you are a single agent playing against someone else, you don't really know what your opponent is going to move after you move. But regardless, they cite chess as an environment where agents know the model. I think they mean that because these engines, these reinforcement learning chess approaches, they play against themselves when they simulate. So if you play against yourself, that means if you play against an opponent that has the same policy as you, then you do know the dynamics of the environment. You do know how likely it is that a state arises from your actions. If it doesn't know, then the agent does not know the effect of its actions. For example, if in self-driving cars, in principle, you don't know if someone will cross the street out of nowhere and so on. Or, for example, playing some video game where there is some randomness. For example, Super Mario Bros. You don't know how likely it is that an enemy appears after moving. So if the agent knows the dynamics and the rewards map, or if it attempts to learn them, because that's something it can do, then we speak of model-based reinforcement learning. And otherwise, we speak of model-free reinforcement learning. DQN is an algorithm for model-free reinforcement learning, and AlphaZero is a model-based one. And as I said, these lines can be a little bit blurry, but okay. So another distinction for reinforcement learning algorithms is what the agent learns. So there's one clear thing that the agent should, one thing that is clear that it can learn, which is the optimal policy directly. So you directly try to find a policy that maximizes the expected return when you start at the initial state of the environment. Here in deep reinforcement learning, so in the recent methods, pi is usually a function that depends on some parameters. The function is a neural network, and then you optimize the parameters by following this gradient. So you just try to take the derivative of this thing with respect to the parameters of the policy and update the parameters in this form. In this case, you want to maximize, so you have plus. But yeah, there's many things that can be said about this. That's just the naive idea. I will not comment further on these methods, but they are a big part of model-free reinforcement learning. Other methods are Q-learning methods, where you try to learn the Q values of the optimal policy. So you try to just learn these Q values. So if you know the Q values of the optimal policy, you easily get an optimal policy. I will explain more about this later, so I'm not gonna give any more details now. Okay, and here we have an overview, types of reinforcement learning algorithms. There's this big division between model-free and model-based. In model-free, there's policy optimization, where you try to directly learn an optimal policy, and Q-learning, where you try to learn the Q values of the optimal policy. There are some hybrid models. Here we have DQN, one of the algorithms that we will explain. And here we have AlphaZero, which is an algorithm where the model is not, for when the model is known. Okay, so let's move towards DQN. So the key observation for Q-learning is the following. It concerns about the value of a state with respect to a policy pi. So the observation is that this value is precisely the expected next reward obtained following policy pi plus the value of the expected next state. So in mathematical terms, this means that the value of S is the expectation of the reward you are going to get following pi plus the value of the next state multiplied by gamma if you have a discount factor. That's just a technicality. This is kind of clear. I think I made a sketch of the proof. It's extremely dirty, but we can check. I think it's easier to. I think that conceptually should be sort of clear, but let's just see a very dirty sketch of proof. So the value of S is the expected return when the initial state is S. Now we can write this return by what it is. It has this form. This would be what appears in the trajectory. And now we move the expectation. We transform this expectation in this form. We remove the first reward. We put it outside. And also we take outside a gamma from the rest of this expression, and we get these two terms. I'm not writing what the expectations are moving on. It has to be controlled, but let's just be very sketchy and not care for now. Well, not care here. Now, this is just the expected next reward plus gamma plus the expected return of some trajectory. This is a trajectory that starts at S1. And now you put all the expectations outside and you end up with this here. This kind of looks like the value starting at the value of S1, which S1 is transformed into S prime, and we get this. So this is the idea of why this works. Hopefully, intuitively, it's very clear that it is true. Okay, so this is the Bellman equation. So this is very interesting because it establishes a relation between all the values v pi, and moreover, it's not any relation. It's a linear relation. Each one of these equations, this thing in here is a linear equation involving. It is a linear expression involving values of states. Remember, expectations are just, you can think of them as weighted sums. So this expectation is really just a weighted sum of several values of this form. So this thing in here is just a linear equality involving this. So this means that if you have a policy and you are interested in knowing the values, you can know them just by solving a system of linear equations obtained by writing this for all states. This can be unfeasible if S is too large, but anyway, unless it is extremely large S, there are other methods that don't require you to solve this system directly. You can use methods from so-called dynamic programming, and it's quite fast. So you can find the values of a policy, assuming you know the model, assuming you know rho. Note that if you don't know rho, so if you are in a model-free setting, you cannot transform this into a weighted sum because you don't know what these probabilities are. But if you do know, and the set of states is not too large, it's not difficult to find all the values with respect to pi. Also, the set of states has to be finite, of course. If it's infinite, it's another thing. Okay, so look only here for now. There's a similar Bellman equation involving the Q values. It's very similar as before. The Q value of SA is the expected next reward plus the expected Q value of the next pair, of the expected next pair. Here it just says what I explained about the Markov property and chess and MDPs not being Markovian sometimes, but still some of these algorithms still work reasonably well, even if they are not fully Markovian. Let's move on. So now we are interested in the Bellman equation of an optimal policy. So recall that the optimal policies are denoted by pi star, and they are defined as the policy such the expected return starting at the initial state of the environment is maximal. So let's start with this observation. The optimal policy is deterministic, and for each state, we have that the action assigned by the optimal policy at that state is the one with the highest Q value, according to pi star. So this is clear if S is the initial state, right? Because pi star is a policy that has to maximize the expected return. And Q pi star SA is the expected return if you start at 0 and take action A as your first action, right? So if pi star is to be the best policy possible, you have to take, at the first move, you have to take the action that is going to give you the maximum reward, so the maximum Q value. And it is easy to see for any S, assuming that you can reach the S. If you cannot reach the S, then this is not true. But if you cannot reach it, you could think that it's not there. Just a technicality. So let's assume all states can be reached by the optimal policy. So the idea is that it's clear for the initial state. For any state, it follows from the Markov property. If you are following the optimal policy and then you reach some state S, you want to continue behaving optimally. When you reach state S, it doesn't matter what you have done so far because of the Markov property. So what you have to do is just pretend that the initial state is S and choose and do as above, do as in here. Choose the action that is going to maximize the expected return if you start at state S. Okay, so here we have the Bellman equation for the optimal policy. This is the one. Where is it? I didn't write it down. Okay, so here are the Bellman equations for an optimal policy. We use this observation here to derive them. Basically, I mean, it's just write down the definition of the value of the optimal policy according to the Bellman equation, and you just note that sampling according to pi star is taking the maximum action. So if we look here, if we replace pi by pi star, the optimal policy, this sampling in here just becomes take the maximum action. So this thing, if you replace pi by pi star, becomes this equation. And similarly, you obtain the Bellman equation for the Q values of the optimal policy. The Q value of SA, if you follow the optimal policy, is the expected next return plus the maximum next Q value possible in expectation for the next expectation over the next state. Okay, so this now the core of Q learning, of the Q learning methods, is the following. The Bellman equation, this Bellman equations gives us a method for quantifying how far a policy, pi hat, is from the optimal policy, pi star, without knowing anything about pi star. Why? Imagine that our policy, which is a candidate for being optimal, is really optimal. Then it satisfies the Bellman equation for the optimal policy. So this is true for pi hat. This is the Bellman equation for the Q values of the optimal policy. But I replaced the optimal one by pi hat. Okay, so we have pi hat. So the closer pi hat is to the optimal policy, the closer these two numbers here and here should be, right? So we can now define a Q loss for a pair SA to be the square of the difference of these two values in here. If this loss is 0 for all SA, then it means that pi hat is the optimal policy. And if it is very, very, very close to 0 for all SA, it means that pi hat is very close to the optimal policy. And you see, we know absolutely nothing about the optimal policy, but still we are able to approximate it. Moreover, basically what we want to do now is to minimize these LSAs. And if you see, there's the only place the policy appears is in the Q values. The only effect it has on this formula is here in the Qs. You don't really you no longer really want to find pi hat. You are just trying to find these Qs so that these values are as small as possible. So in the previous equation, pi hat does not play any direct role. We only care about the Q values. If you can find the Q values such that that loss is 0 for all SA, then you find your optimal policy, which is just choose at each stage, choose the action with the highest Q value. So now we can forget about pi hat and simply learn a map Q from pairs state action to R, such that this thing is as small as possible. Here I simply replaced Q pi hat by Q, our abstract function. See, if the model, as I said before, if the model is known and it's small, then you can solve this efficiently using systems of linear equations or using dynamic programming methods. But we are interested in the case where it's model free, so we don't know rho, and the set of states, actions, and rewards is very big or infinite. Okay, and one last thing. So now we are getting close to the DQN algorithm, but just some words about finding these Qs. So we are looking for these maps that satisfy that those L's are small. And we are assuming that S and A are very big or infinite. So in deep reinforcement learning, what it is done is Q is a deep neural network, which depends on some parameters alpha. Now we put the parameters as a subscript. States and actions are represented as real valued vectors or tensors. And you use gradient descent to minimize these L's. It's not clear. I will explain next talk what SAs you have to choose. And you cannot really minimize this L because, as I said, you cannot compute this expectation if you don't know rho. But we will, answering these questions will lead us to the DQN algorithm next talk, next week. And thanks.
Thank you very much, Albert. Is there any question for Albert? Well, if not, I would say to thank you him again, please.
And thanks.
Thank you.
Okay, see you next week.
Bye.
Bye.
Ciao.
Ciao.
Bye-bye.
Bye.